This is the work that I do in collaboration with a lot of people, young researchers. I'm very proud of this team that basically started working with us very recently. You may know some faces if you have been to SETI Institute, if you've been watching some of our talks. Tom Esposito is kind of my number two. He's the project manager of the science team at Unistellar. Paul Daba is leading now the Exoplanet science mission. Lawrence Bro lives in Atlanta, but she does work with us. She's kind of our communication specialist. Ryan is studying planetary defense. Ariel Gregowski, she's studying comets. And Daniel is our education specialist. You may see him coming here from time to time in the future, especially if I heard you acquire a Unistellar EVScope. So we are a local company. Unistellar is a French-based company. The co-founders are French. I'm one of them. But we have a company in France that manages the company itself, meaning logistic, manufacturing, development of the app, etc. But here in United States, we have an office in San Francisco, which is the SETI/Unistellar office, where we have all these researchers, and we do citizen science, as education, outreach, communication. We're very proud of that. So let's show next slide, please. What's the Unistellar network? So I'm assuming you all know what is a Unistellar telescope. Who have not used a Unistellar telescope here? 1, 2, 3, 4, 5, 6. Okay. So Unistellar telescope is what we call a new generation telescope. It's a digital, smart, robotic telescope. It's a relatively small telescope. I should have bring one with me today. It's typically 10 kilograms, 4.5 inch. It's this size. You carry it in a backpack. And thanks to the Unistellar telescope, you can basically, and that's the goal of the Unistellar, you can enjoy the dark sky in less than 5 minutes. If you watch videos on YouTube, you learn how to use the telescope. You control it with an app. You connect your app to the telescope. The telescope will know where it's located, the time. You press a button, it will orient itself, find where it's looking at, and then give you a list of targets you can observe. That's basically the principle. Making sure that people can observe galaxy nebulae even from cities. We have a sensor on board, we remove the pollution, we process images, and you can see on the phone an image, like if you have a 1 meter plus telescope in your backyard, and you see in color. So we have two models at the moment, the Equinox, which doesn't have an eyepiece, and the EVScope 2, which has a digital eyepiece. They're slightly different in technology. The Equinox is kind of our first generation. The EVScope 2 is a new generation EVScope. So you observe, you're having fun in your backyard, you show galaxy nebulae, you watch comets. The app will tell you when there is something interesting in the sky as well, like a scientific object passing by, such as an asteroid, a supernovae, etc. That's what we call citizen science, and that's what I'm going to describe to you today. So when you observe, you collect data, like any digital device. It's a kind of a camera, and these data, those frames, can be sent to us, the Unistellar SETI cloud, and we process the data for you. And that's what we do at the SETI office on a daily basis. So next is basically some images of what you can see in the Unistellar network, the Unistellar telescope. This is what we call an enhanced vision images. So this, in this case, we stack on the left on the galaxy, and I forgot the name of this one, shame on me, but I've completely forgotten. So sorry. It's not a triangular, it's something else.
Is that pinwheel? Or,
a pinwheel, yes, that's a pinwheel. Someone should know the coordinates. If we had an astronomer in the room, he should be able to do that. Right?
Yeah.
I think it's a pinwheel. So here we observe 46 minutes of pinwheel galaxy with the telescope. We stack thousands of observations, you rotate them, etc. There is on board a computer that analyzes the image, remove basically imperfections, improve the sharpness. We're using, it's not magic, we are using basically what astronomers have been using for years, but we do it in real time with a small device. We see in the middle here a comet. That's NEOWISE, the comet that flew by Earth a year and a half ago now. You can see the sodium coming from the comet, and here we have a nebula that you can observe. You can see the hydrogen gas on this one. So you enjoy that, you observe this with your friends, it's fun, there is thousands of objects in the app. And frankly, I calculated, if you live more than 200 years, you will not be able to observe all the objects in the app. Okay? So you buy this telescope, you can use it for life. But, next slide please, we want people to be more than just do more than just observing the dark sky. It's a good thing to observe the dark sky, but we have noticed that people can do more with our telescope. We want them to become citizen astronomers, meaning that we want them to contribute meaningfully to science and to be part of the scientific conversation. So for that, we created this device, but we also implemented a website. So you can go on unistellar.optics.com or unistellar.com. We just switched today, in fact, to unistellar.com, and you will see, if you click on science, some kind of list of scientific activity you can do. And if you go on your app, there is a menu, scientific menu called Scientific Observations, and inside this app, you can see on the right some scientific activity. Let me describe some of them in detail later on. Next, please. So this is a map of our users, and it's not a complete map. In fact, I noticed that there is a lot of points missing because I shipped some of the telescope myself. We have just now, for instance, a telescope that arrived in Mongolia. We have a telescope in China. We have multiple telescopes in Morocco. So here we have a network of 10,000 telescopes. We know that because of the manufacturing. We know we manufacture, we know the number of telescopes we have manufactured, and we know that this number is growing on a daily basis. Among these 10,000 telescopes, not all of them are citizen astronomers. We have approximately 1,000 now citizen astronomers, people who want to contribute to scientific investigation using the telescope. And each of them, some of them have specialized in some specific scientific activity. You may notice that we have a lot of points in the Western world, of course, in United States, Canada, and Europe. We have a lot of users as well in Japan. They love our device because Japan has a high-density population with a lot of light pollution. But beside this, thanks to our telescope, you can observe galaxies from Tokyo, which personally astonished me when I went there, because Tokyo is extremely bright, because it's a gigantic city of multiple cities. We are now shipping as well in Australia, New Zealand. The New Zealanders are extremely active. They are creating their own network of citizen astronomers between themselves. We are shipping now in South America. We have a distributor there. We have shipped in Russia as well, and India. So the network is growing every day, and more people join us to do science. Next, please. So who are these people? Well, they're people like you and me and more. We have amateur astronomers, so people who used to have a telescope, adopt some large telescopes, and then switch to the digital technology because... So those people are amateur astronomers, I mentioned. We have students, a lot of students from university when they have their own telescope. Urban family, so people living in cities. In San Francisco, I think we have more than 50 EV scopes. Now I cannot go to a park without seeing an EV scope when it's clear in San Francisco. Because it's very rare it's clear in San Francisco. So when it's clear, you see an EV scope somewhere in the street. We have people who like the outdoor, or live in those nearby those dark sky area. VIPs, we are scientists. A lot of my colleagues, despite the fact that they have used 8-10 meter class telescope in the past, are now using the telescope, this telescope themselves. And in fact, I'm going to confess something, is since I had this telescope, I'm observing way more than what I used to do when I was only a professional astronomer. Because now there is something in the sky, I take my telescope, I put it out, and I observe it. Before, I had to write a grant proposal, ask for time, go over there in some cases, etc. And I have like 5 minutes of observation, and I was crazy about it. Now I have so much data with this telescope that in fact I have more data that I can process. And that's going to bring me to the next part. So, next slide. I'm going to have to accelerate a bit. So, Unistellar is a private company. We have an agreement with the SETI Institute, the non-profit organization located in Mountain View. SETI is the main scientific partner of Unistellar, meaning that we have access to the Unistellar data, and we work with the Unistellar team in France to develop the scientific activity and education activity. SETI is not doing this alone. We have 5-6 scientists, as I show you, but we all work with we have colleagues around the world. So we do work with MPC, the Minor Planet Center, we work with NASA TESS, AAVSO, the Lucy mission, the Observatoire de Paris, Charles University in Prague, IOTA, and recently we have now as an official partner the NASA, because NASA basically gave some funding to SETI Institute to develop the network for exoplanets. Next. So, these are movies, they're running, perfect. So I'm not going to be able to talk to all the science we do with the Unistellar network. I'm going to describe a few of them. So asteroid occultation, it's basically to observe an asteroid indirectly. What we do in this case, we look at a star and we see the star disappearing for a few seconds, or even tenths of a second, due to the fact that an asteroid is passing between us and the star. This allows us to derive the size, shape, the presence of a moon or rings around an asteroid. So we do that now on a daily basis with the network. The next one is planetary defense. In this case, we wait for an asteroid to fly by Earth. We have, for instance, the recently discovered 2022 RM4. It's a 600 meters asteroid which was passing at 10 times the distance Earth-Moon. It's interesting because it's a large NEA, near-Earth asteroid. And using our network, we can observe it, derive the position of the asteroid. So we find the orbit and measure as well the variation of light, so derive the spin of the asteroid. And in some cases, where we have a full coverage for multiple weeks, we can also derive the shape of the asteroid. So we have done that, for instance, for 1999 AP10 last year. We're going to talk more in detail about exoplanet transits and cometary activity. And in fact, this slide was a week ago. Now, if you go next, or you press, we have now 5 scientific campaigns. And here I'm going to announce, in fact, that we have a 5th one coming, which is the observation of transient event. I'm going to go through that too later. Next. So, let's go to some of the main scientific results of the last 2 weeks. And I'm really talking about the last 2 weeks here, or 3 weeks in fact. Which is kind of it's impressive to me that what we can do now with this network in a few weeks. So NASA launched a space mission, DART, to an asteroid called Didymos, and Didymos has a moon called Dimorphos. This moon is a small 200 meter diameter asteroid. So this in fact happened on September 26 at 4 a.m. in European time, because I was in Marseille at the time, and we did basically a live show at the SETI Institute with our network. And we have some observers in Africa. We have Patrice Huet, that you can see on the left here, who observed from Réunion Island. It's an island close to Madagascar. It's a French island, but it's still in Africa. And using this telescope, if you click on this movie here, it's going to be in French, but that was the first result we got live. You can see the line of the asteroid moving, and thus at the impact, we distinguish this kind of fuzzy blob appearing. And you also notice a change of the color of the asteroid. So this is basically the impact of the DART mission seen live from Réunion Island using an EV scope. And we have done that from other places. Next, please.
That's cool.
Here we have from Kenya, Susan Murabana from the Traveling Telescope Company. She organized a star party the night of this event. So click on this movie, please, on the right. And look at this.
Whoa.
Very cool. So when we saw that, frankly, we did a show, as I said, live show. We invited 15 scientists involved in the DART mission, and we asked each of them what they think we're gonna see.
How bright.
And how bright will be the decrease of magnitude, remember? And in fact, I was the super optimistic one. I say 3 or 4 magnitude. And we had 2.7 magnitude. Yeah. So it was incredible. I was not expecting that a small mission the size of mini Austin will make such a huge impact on the surface of an asteroid. So what is incredible is that people around the world could observe this with the EV scope. And I think this is the main reason we created this technology, is to bring back the astronomy to people, to let them be able to observe it, to witness what's going on in the sky at the moment. Because a lot is happening right now. We heard about planets, exoplanets, etc., but we also now can see satellites. We can see activity on space, like the design, the building of the Chinese mission, for instance, can be observed with the EV scope. So this is kind of the reason we invented this telescope. And one of the things that I really always wanted is this telescope to be international, to be everywhere. So having that from Africa, especially from Réunion Island, which is the country where I'm from, was something very important to me. Okay, next, please. So with this telescope, because they're all identical, okay, we have 2 types, remember? It's very easy to kind of put together the data. We don't have to deal with people having different type of focal plan, different cameras, different noise on the camera. All of this is not a problem to us because you have 2 types of cameras and 1 type of telescope. So what we do sometimes, we tell people, hey, there is this bright object, in this case, comet. The Pan-STAR K2 comet was basically visible in July and August, and getting brighter. It's still getting brighter at the moment, but in the southern hemisphere. So we organize campaign in the northern hemisphere. So we ask our users to observe it the same time, the same day, the same night. And we can put together those observations to create what we call a super image. So it's like if you create, we observe a Pan-STAR with a 2, 5 meter, 10 meter class telescope by simply putting together the data from all those small telescopes. And the advantage of that is that we also have people located at different locations, so we avoid the issue of having bad weather. So this is some of the observation of Pan-STAR we collected. On the left, you see an observation from Europe, and on the right, you see an observation from Japan. On the top, Europe and North America. And what you can see is the change of activity of the comet. Once again, we are witnessing, thanks to this telescope, what's going on, what's happening in the sky. You can see the coma, you can see the tail. You can see that the tail is the combination of the solar wind. The sun is in this direction here, and the comet is going down on this diagram. So the tail is slightly tilted because it's being pushed by the solar wind, and you can follow the velocity of the comet. Comets are amazing because we cannot predict what they will be, in fact. And that's, next slide, please. That's what we try now to do. It's a bit technical here, but we now ask our users to observe regularly comets. And we put the brightness of those comets on those diagrams here. As you can see on the left is a cluster of points taken almost together in July. And on the right, the same data, but with a few additional points taken before in April using our telescope. So these kind of figures here is basically a way to predict for us the magnitude of the comet in the future. So K2 was extremely bright in July, August, but now we have a better modeling of the brightness of the comet. And the reason it matters is because we have a new comet coming soon, E3, 2022 E3, and it's going to be extremely bright, maybe in January or February, maybe visible with naked eyes. So what we're doing, we're observing it now. So we refine this kind of orbits so we can do a better prediction for you. And we hope that we're going to tell you in the next week whether or not E3 is going to be visible with binocular or with naked eye. So this is work in progress thanks to our community as well. Next, please. Okay, I'm going to accelerate and talk about something that I really think it's amazing to can do with this telescope. So you know now when you look at the sky, you don't see stars, you see planetary systems. Because we know that each star in our galaxy has an average 2 planets. So the galaxy is full of planets, 400 billion planets. We are studying those exoplanets, that's what we call them, using different technology. I spent years developing instruments to image exoplanets. If you click on the left, you already click on the left, so it's starting, you can see an observation of HR 8799, a planetary system with 3 more, but here we see 4 exoplanets orbiting around the star. On the right here, when you click on this one, you can see 51 Eridani b, the first exoplanet similar to Jupiter that was directly imaged using an adaptive optic system in 2015. In 2017, I gave a talk here where I showed that. So you already know about this, so I don't have to talk about that. But my point is that we can image exoplanet in some very specific cases using those gigantic 8 and 10 meter class telescopes. But there is also another way, next slide, to observe exoplanets, is not by observing the planet itself, but by detecting the shadow of the planet as the planet is passing between us and the host star. This is what we call transit. In this case, from the shadow of the planet, can you click on the brightness diagram here? You know that because you live in the Bay Area, you have probably seen gazillions of talks about Kepler and TESS. So we see what we call a lie curve. And the lie curve shows a dip here in brightness because of the presence of the planet passing between us and the star. From the dip, you can derive the size of the planet and the orbit of the planet. So you can basically derive the existence of this planet as some information. Next, please. So a few months ago, we got good news that NASA decided to fund our project to observe and to characterize and confirm exoplanet detected by TESS. So TESS is this mission that's been launched 3 years ago now, and TESS observed the sky almost continuously, a different part of the sky almost continuously, and has already detected 5,000 exoplanet candidates. So we're talking about planets, the signature that I just mentioned to you, like the Stanley attenuation of the brightness. But those are candidates because in astronomy we prefer to have multiple observations before confirming the existence of an object. It's not because we see a small variation, we're going to scream, oh, there is a planet here. Well, some people do that. But the real astronomer, what they do, they say, well, let's take another set of data a few days later, or a few weeks or years later, and see if we see the same attenuation. And in this case, we will confirm that this is a true planet. So we have 5,000 candidates in a catalog of tests that are waiting to be confirmed. And there is not enough telescopes in the world to do that, except the Unistellar network. So what we did, we basically sent this project to NASA, and they funded us to follow up some of the test objects of interest, TOI, and I use this term a lot, so those are planet candidates, and to confirm their existence. We have a catalog of 100 planets to be confirmed with tests at the moment. And we have a second program which is to do the same, but focusing specifically on the long duration exoplanets. Those are Jupiter-sized exoplanets, far away from their star, that we want to confirm. But this kind of transit happens once every 3, 5, 10 years. So we need to have basically several instruments to be able to confirm the existence of this planet. So I'm going to describe this in more details here. I may skip that just to extend you. Next slide, sorry. What we need to know, what we want to do here is to understand how solar systems or planetary systems form. We want to be able to refine the ephemeris, meaning the orbit of the planet, so we can tell to astronomers when there will be a next transit. And we want also to have a better understanding of what type of planet exists in our galaxy. And we can do that with the Unistellar network. I'm going to show you a few examples here which are kind of new. So how we do this? Next, please. Well, it's extremely boring. And that's one of the reasons I don't do a transiting exoplanet. I let other people do it for me. Because it's extremely boring. You basically take a telescope, you go outside, you choose the planet, you click on it, you observe, you let the telescope record data for 3, 4, 5 hours. You can watch Netflix or do something else in the meantime. Because we do have now a guiding that is extremely accurate, so you don't have to stay outside in the cold with your glass of wine or your tea. We did that basically 2 months ago, and I think that was one of the best presents we gave to our citizen astronomers. Since then, we have a ton of observation of exoplanets. So, you observe the field of view like that. If you click here, you're going to see some very boring animation. Where basically what we do, we measure the flux in the star that's going to be potentially occulted in blue, and we compare with the flux of a star nearby which has not been occulted. Very simple data analysis, if I describe it like this. But next, we are trying to observe things which are extremely faint. Okay? So here we tried to observe HD A0606b, and I'm sorry for the names, but that's also called the scorched planet. It's a planet for which we have detected 2 transits, and it's an extraordinary system because it's a planet which has an extremely eccentric orbit, and every, I forgot the exact period, every 6 months roughly, we can see a transit, an attenuation. So this animation shows we predicted when this will more or less happen. We have an idea plus or minus 27 hours when the occultation, when the transit will happen. So we asked our network to observe it. So Masao in Japan observed it. Petri in Finland did it. Bruno in France did it with 2 telescopes because he has 2 telescopes. Don't ask me why. Michael is in, where is Michael? I forgot. Kevin and Alexandra are in California. So those are, I know those people now because we work a lot with some of the citizen astronomers. They observed and they saw this dip, the attenuation. So they confirmed the existence of this planet. Can you press the slide? You're going to see an animation popping up. These are the real data, okay? It's not easy. You observe, you take thousands of frames, and then you basically stack them together, you arrange them together so you can detect this attenuation of 1% in this case. Wow. So when you observe with us, you're part of this kind of campaign, we send you a few weeks later this kind of diagram where you can see the detection of the exoplanets. This is a difficult case because it's a transit for which we have a huge uncertainty in time. So we ask these people to observe almost continuously for 27 hours. And that's something we can do with the Unistellar network that nobody else can do. We can observe continuously using the rotation of Earth and using the fact that we have thousands of telescopes around the world. Because what you see here is the pretty picture, right? Basically the positive detection. Remember that Pavlov, which was in Russia, that you don't see on the map, he could not observe because it was cloudy from his side. A lot of people tried to observe it and it failed because of the weather, because something happened. So here we show you the positive detection. Don't forget that behind those positive detection, there is probably 3 times more attempts to observe it that did not result in a positive detection because of technical or meteorology forecast, weather forecast reasons. Next. This is another cool planet. It was basically completely off. The orbit was off. That does happen. That's TOI 3799.01. Nice name again. So this one, there was a prediction of when the transit will happen. We always ask people to observe 3 or 4 hours before. And in fact, that saved us a lot of time because the transit was 1.5 hours late, and we detected that. So next, press again, please. You're going to see another slide. After this detection of the lateness of the transit, we asked our network to observe it again, but this time we adjusted the timing, and we got the detection. So I know this is tiny point in the diagram. It's not exciting. But this is the detection of exoplanets from the backyard of people who live in cities like San Francisco sometimes, so even bigger cities, right? So I will not have believed in 1995 when I was a young student and we had discovered the first exoplanet by radial velocity, that in 2022 we have instruments that will allow people to confirm the existence of exoplanets from the backyard. I mean, it's a gigantic leap here that we have done in technology. And this is not magic, in fact. You already know that. This is technology. This is computer science. This is like the improvement of our civilization at large. And I think it's remarkable that we can now do this using small telescopes. Next. Okay, this was just accepted in publication in the Astrophysical Journal. The lead author is a student of mine, Amaury Perrochot from France. He came here to do an internship for 4 months. And I told him, well, you're going to do something extremely crazy. We're going to try to detect the transit of Kepler 167e, which is quite a well-known planet, but we have a huge uncertainty on the orbit because the orbit of the planet is almost 3 years. We're collecting data last year, and it was very noisy, and a lot of people try, and a lot of people fail to see the transit. In fact, I gave this project to him thinking that he will give up after a week, but after 4 months, he managed to see the transit, detect the transit. It's very shallow, but it's there. It's the longest transit ever recorded from the ground, ever, even with big telescopes. This is like the longest one, several hours, 40 hours of observation in this case.
Wow.
And with that, we have now a better orbit of this planet. We know the orbit with an accuracy of 7 minutes.
Wow.
So that's an improvement because in 3 years, or slightly less now, we will be able to observe Kepler 167e and get more information. For instance, we will be able to tell JWST when the transit will happen. And JWST telescope will observe a different long wavelength and see a different color in this transit, so get some idea of the composition of the planet. And that's the way science works. There's always a small step. First you detect, then you characterize, then you find there is some issues, then you refine the orbit, and in this case we refine the orbit and we have a very good orbit now. We know that we can observe this planet again in 3 years with extremely good accuracy. Next. Okay, planets again. Sorry, this one, the last one. This one was a cool one. So this is the first NASA partnership planet. So it's TOI 1812.01. Not exciting name, but there was some kind of TESS observed it once, observed the transit once, and because of some kind of timing, could fail to observe it multiple times. So we have a model that gives us multiple solutions on when the next transit will happen. One was saying in 71 days, we did not see it. Next. One say in 86 days, it did not happen. And then finally, we observe, our team observed it again, and they observed and they detected after 112 days. So now we know the period of rotation of this exoplanet. We know the orbit of this exoplanet, so we're going to repeat this observation every 112 days to be able to refine the orbit and to maybe see some perturbation that could be indicative of the presence of another planet, or could be indicative of the presence of moons around the planet. But that's remarkable again that now we can characterize those exoplanetary systems. So the next slide is a summary of everything that was done in exoplanet transit. It's a lot of words. I just wanted you to understand that this is not something like I presented you 3 or 4 examples here, but we have done way more. Okay? We have created this community of almost 200 citizen astronomers who are dedicated to observe transiting exoplanets. So if you have an EV scope and you are tired of watching Netflix, or you say, oh, I will watch Netflix, but I want to do something else more interesting and meaningful at the same time, well, take your telescope, go on our website, and you will have a list of transiting exoplanets that you can observe from your backyard. And it's very fun to basically receive a few weeks later, or sometimes a few days later, a light curve. I know it's, again, it's a tiny dot with scribble on it, but it's a signature of a planet, another world over there, another planet that could be the size of Jupiter, but still very interesting because maybe around this Jupiter there is habitable moons, for instance. And that's something that we will be able to find in the future thanks to those kind of observations. So we have also an important point here is that when you do the observation of an exoplanet, we send you the report after a while, when you see the signature of the planet, if it's successful, but you're also part of the scientific community. We basically keep you aware of what's going on with this planet, if there is some interesting discovery, like a shift in period, detection of some perturbations, etc. And when we start writing a paper, we involve you, the citizen astronomers, in the process as well. So we have a Slack channel that we discuss with our citizen astronomers, and then we create a specific one for the one participated to the observations, and they're part of the process of analyzing the data, discussing the results, and they're co-author of the paper.
Yeah, I can vouch for that because my daughter and I are listed in a paper with Dan that we helped to do for an exoplanet.
The huge paper by Daniel with 100 exoplanets.
Yep.
Good.
So you definitely get listed as providing data. It's very cool.
So you become a citizen astronomer.
Yeah.
That's really, it's important to us that people are involved in the entire process, because it's not only about doing astronomy, it's about involving everybody in the scientific process, in the scientific discussion. Next. Okay, I'm going to go super fast because I have no idea how much time I have here. So this is the new transient event campaigns that we just started. In fact, it's going to be released on November 15 on the app. So if you click here, you will see a pretty animation showing you what is a transient event. A transient event is an explosion, most of the time, of an object. It could be a nova, a supernova, detection of gamma ray burst. The universe is full of this extremely luminous, energetic process. Explosion of a star, encounter between multiple neutron stars, etc. And those happen randomly in the sky. We have surveys that look for them at different wavelengths. Sometimes we see them with a space telescope in the UV, but then we don't see the afterglow, we call that invisible, because we miss it, because there is nobody watching this part of the sky. So what we want to do is to give you the opportunity to know almost in real time when something happens in the sky. Next. So we are beta testing this. Next slide, please, sorry. We are beta testing this at the moment. We're starting in June. And we already observed multiple supernovae and novae. I'm going to show you a few examples here. the goal is that when you're going to have your phone, you're going to receive alerts when something happens in the sky and it's visible from your house. So we know where you are because we're basically going to have some information about our citizen astronomers who want to participate to this, and to make sure we are not bombarded by thousands of notifications in the future. We're going to curate them, select the most interesting one. The reason we're doing this is because there is a huge project coming soon called the Vera Rubin Observatory, LSST was the previous name. It's going to have its first light in 2024. It's an 8-meter-plus telescope that's going to observe the entire sky every 3 days. In southern hemisphere sky, but part of the northern as well. We expect this survey to provide thousands of alerts every day of things popping up in the sky. Could be, as I say, supernovae, novae, could be intelligent civilization telling us they are here. Could be anything, but most of the time, if you want to understand those transient events, you need to observe them at multiple wavelengths and continue to observe them for a long period of time. So we are going to be able to do this, we believe, with the Unistellar network. Next. So this is the first example. It's a nova. Sorry, I forgot to say next for this. So that's exactly what I say. So next. Sorry. So that's a nova. Scorpioi is basically a binary system with a white dwarf and a red giant. And regularly, one of the outer envelope of the white dwarf explodes due to the fact that it's swallowing the red giant. It's not really my field, so that's a field of Tom. Tom is our stellar astronomer. But what we did with this is that we get a notification from the Alert system, which is an alert system connected to Squeaky, and the ZTF, if you prefer, and we asked our users to observe it in June 2022. And so what you can see on the right is basically a drop of 2.5 magnitude over less than, if I remember, what is it? Few days, 1 or 2 days of this nova. So that's the validation that it's possible using the Unistellar network to do this kind of observations and provides meaningful scientific observation as well. The goal for us is because we have a global network that can observe the sky anywhere, there will be always, I try to phrase that the best way possible, but I still don't know. I'm going to improvise again. There will be always a starry night in the Unistellar network. So that's in reference to the British Empire. What was it?
The sun never sets in the British Empire.
Okay. But in our case, there will be always nicer than the British Empire. Because we don't use people. Anyway, I'm not going to go through that French. Sorry. Give it this for me. There will be always some stars visible. The star will be always visible somewhere in the Unistellar network. That's what I'm going to say. That's the best way. Meaning that anywhere, if something happens in the sky, detected by ZTF or LSST or one of these large surveys, we want you to get a notification in less than a minute that this is happening. So you observing, you get the notification, boom, you observe that, and maybe you'll be the first person to receive and to record an extraterrestrial signal coming from a civilization. Or maybe you will be the first person to witness one of the closest supernovae. So that's pretty cool. And that's very challenging. There is a lot of computer network here that we have to fix, but we are ready. We are launching this November 15. We're beta testing that in the app, and we hope to have people observing that. And the cool thing is that we started this in June, and we already get 2 observations per day for this program. So I think there is a strong interest from the community of citizen astronomers to do those kind of observations. Next, the next slide. It's a good news and a bad news as well. I took that from my technical report from Unistellar, so I didn't rewrite the text. But the good news is that we have a lot of observations taken by our citizen astronomers. We are exponentially growing. It's a good news for most projects to grow exponentially. It's also bad news because we are going to soon reach a point where we're going to get so much data that we are not going to be able to process them. So we expect this to happen in 1 or 2 years. So we're getting ourselves ready for that. We can boost our servers. We can beg for more money to the AWS or find a rich founder that can help us, or we can get smarter. And I think we're going to go through the route of getting smarter and doing more machine learning analysis. In fact, we are starting for the occultations. We have now an algorithm that analyzes the data in machine learning to detect whether or not there is a signal, like an attenuation of the star. And if that's the case, then run the data processing. So that's something we are working on, and we hope if there is some people here who want to do an internship in, have some good training in machine learning, data science, and want to do an internship, we are going to hire this year. Next, please. So, more than Unistellar, the goal here is to create a community of citizen astronomers to bring back astronomy, but also to make people do science to understand science. And I think that's a true new revolution that we are going to see soon, not only in astronomy. It's getting easier and easier to do science. It's getting easier to get instruments capable of recording earthquake, measuring the, collecting data, forecast data. It's also now easier to collect these data and to analyze them. So I believe that despite everything we can read in social media, especially in the press in general, the world is getting better in terms of being more savvy, scientifically speaking. And it's extraordinary that now we are in this moment where we can harvest this scientific interest from people. Instead of having 100 scientists doing astronomy, we are going now to have 10,000, 100,000 of them doing astronomy. Observing the stars, processing data, learning about objects in the sky. And that's going to be the revolution because there will be a lot of discovery, I anticipate, coming from these people. A lot of the people who are doing now observation with the Unistellar network are going to probably get interested in some specific objects. And I'm hoping, and in fact I'm starting seeing it, that some of them will become astronomers, professional astronomers. Or some of them will switch their interest and use what they learn in data science to do more data, to bring the data science to astronomy. So more discoveries, a world which is basically more focused on observing up instead of observing down. Mm-hmm. And that's what we call the new astronomy. And that's something that Unistellar, the SETI Institute, and other institutions in the world wants to basically develop. It's not only a movement, it's truly kind of an ideal that we are trying to put together in other institutions. Next, please. I want to mention this because this is one of the critiques we get when we started this project. It's an expensive technology. Yes, when we did the Kickstarter in 2017, the telescope was at $1,500 more or less. Who bought the telescope at the Kickstarter?
Ed did.
Ed? You did, right? Yeah, thank you. You're one of the 2,000 persons who totally believe in us, yeah, without even knowing us. So I find that admirable, by the way. 4 French guys putting together a website saying we're going to change astronomy by building this telescope. So you know, I don't know if I ever mentioned the story to you here, but when we did the Kickstarter in 2017, I showed the telescope, the prototype. You have seen the prototype before?
Yeah, I saw it.
The first one was the ugly piece of crap, I will say now. It was I used to call it the Frankenstein telescope. It was made of pieces of the telescope, right? And I used to bring it to star parties. I brought it once here, and to plenty of other places in the Bay Area. And in November 1st or 2nd, we did the Kickstarter. And I'm the one who was switching the website to start the campaign at exactly 7 a.m. Because the Frenchie wanted to start at 7 a.m. Pacific time, because for them it was 4 p.m. of course. So the story is I was in my bed with my son, explaining to him what I'm gonna do, and I switch the website, and I look at the Kickstarter page. I say, what's going on? It's not working. In 2 minutes, 150 telescopes were gone. And I was 100% sure that it was a bug in the system. It took us a long time to realize that we somehow had managed to convince people that buying online a telescope that does not exist, that most of them had never seen, will be a good investment. So thank you, Ed. Because I think it was a good investment. We still use your telescope, right? You just told me that. So when we start manufacturing at bigger scale in 2019, we delivered the first telescope. It took 2 years. The reason it took 2 years, probably you don't know this, another story, is that we had a bet. My bet was that we will sell 64 telescopes. And Arnaud, another co-founder, was extremely optimistic at 120-ish or something like that. So when we get like 2,000, it took us very by surprise. We were all scientists in various institutions, so we had to basically create a real company. Because when you want to manufacture 100 telescopes, yeah, you can do that in a big hangar somewhere in France. But when you have to manufacture 2,000 telescopes, that's another problem. We have to scale up. And that's why we created Unistellar as a big company. We hire people, engineers, etc., production in China. It took us a long time. And that's the reason you receive a telescope only in 2019. But then when we started manufacturing, we realized that selling telescope like this at $1,000 will not be sustainable for the company. So the price increased to $3,000, and the telescope tuna is $5,000 plus or minus 500. So it's an issue, and we realize that because it looks like an object for the wealthy, for the rich only, and it's not really what we wanted at the beginning. So we tried to go around this by getting support from foundations. So we got a grant from the Moore Foundation to deliver telescope in community colleges around the world. That's what we call the UCAN project. The SETI Institute education program is involved in this. So we are building around the telescope as well education program for instructors, for professors. So meaning that they will basically, we create a network, they are connected with each other, they receive a telescope, and we also design educational tool for the schools. So if you get an EV scope and you have your students, you basically in a few minutes, you go online, you know what to observe. We give them tool with project-based instructions, etc. So that's the next big things for us. I will say next slide, please. We want to develop the UCAN project to a bigger scale. We have now 31 telescopes, 31 colleges in the US who received an EV scope and using them. We want to train the professors, so they train their students in the future, and the students learn about astronomy and participate to our scientific programs. The reason we want to do this, it's also because this is another belief that I have, is that I believe that the space industry is going to be the next big industry for the next 45, 50 years. And we're going to need a lot of people who understand the difference between an asteroid, a galaxy, understand how to calculate orbits, have done at least once in their life an observation with a telescope. Even if they work in floating hotels in space, or they go to the moon, they will need to understand that to work. So to create this workforce in the US specifically, we have developed this UCAN project. This UCAN project is basically that, bringing astronomy in community colleges everywhere, bringing astronomy in all the places for underrepresented group, for all the students in the US and elsewhere. So if you are part of a college and you want an EV scope, remember that we do donate those telescopes as well to educators. And I'm going to finish with this conclusion, a multiple conclusion, but this is kind of a summary. Next slide, please. So I show you the success of our program. It took way more time than I expected, but the main point here is that with an EV scope, it's not only a telescope. it's a community. You're part of a community. You learn. You learn to observe. You learn to analyze your data. You take data, scientific data that will be used by scientists around the world. We have observed hundreds of exoplanets so far. With this telescope, you can also save the planet, be part of the planetary defense program. You can observe comets, enjoy and get surprised by those beautiful bodies that appear in the sky and disappear sometimes dramatically. And soon you will be able to even see supernovae. I mean, that's kind of, I will have no other word to say, but it's kind of cool that you can from your backyard see a supernovae which exploded probably 20 million years ago and wiped out probably civilization in this galaxy around them. You can see that from your telescope. So thank you very much for those who supported us in the past, and for those who who don't have yet a telescope. If you want to buy a telescope, I recommend you buy a Unistellar telescope. Thank you.